All right, I'd like to tell you the story of conventional current flow versus electron current flow. If you're here, it's because you've heard both of these terms and maybe you're a little confused about the difference. It is a bit of a confusing topic. It leads to questions such as which one is the correct one? Are some circuits conventional flow and some electron flow? And why is this a thing? Why is there confusion around this particular issue? So I'd like to take a few minutes and explain it to you. One of the issues is that it's hard to know when to tell you this. You do need to understand a little bit about electricity before you can understand the differences here. So if you understand resistive circuits and diode circuits, then the few minutes you give me here will probably straighten you out on this. If you go through it and you don't understand it, then my suggestion is that you come back a little bit later once you understand a little bit more about electricity, and then I think these few minutes will make some good sense to you. So it goes back to the discovery of electricity, and one of the guys, for instance, was Ben Franklin, and he was flying a kite, and he observed that in a thunderstorm, his kite was struck by lightning, and it appeared that something traveled down the wire attached to his kite and manifested itself at the ground. And okay, this was electricity, and it's some sort of a force. There was some debate about what it actually was, but clearly you had something that was, moving to something else. We had the lightning that, I mean, they saw it with their own eyes. It looked like it came from the lightning and it went down the wire to the ground. So this was something moving to nothing or something moving to a vacuum. It's like water running downhill kind of a thing. And so this is how they described electricity as they were, you know, uh, discovering things and experimenting in the very early days. Then we learned about electrons and atoms and how that works. And you've learned about this, and you know that when an atom gives, or when a molecule gives up an electron, an atom, sorry, um, it's the electron that is going to move to find a positive potential, which is typically the hole in another atom that has let go of an electron. And so we understand that that's electricity. It's these electrons negatively charged that are going to find this relative positive charge over here. And so this is electron flow theory, and you should be fairly familiar with that by now. And the old way was referred to as conventional current flow. So you may ask yourself, well, why didn't we simply say, okay, well, now that we know how atoms work, we know that it's electrons that flow, so we'll all agree to go with electron theory. And I don't really have an answer for that, except that conventional flow was well entrenched, if you will. It was taught in all the schools. It works well to explain it. And in retrospect, if you take a look at this from an atomic point of view, we talked about an atom that lost an electron, and we talk about the electron moving around. But this thing here is what is known as a positive ion. And so while the electron is going to be going to looking for positive, um, like for the electron is going to look for a hole, it's going to look for that positive. The positive ion is going to look for a negative ion. And if you look at it from an ionic level, then yeah, it adds up all right with electron flow theory, but you can see that we're sort of at different levels. And intentionally, when I'm teaching this stuff, I stop at electrons. For one thing, it's enough if you look at it from an electron perspective, it's enough to understand semiconductors and electricity and anything else that you may need to know as a technician. And in actual fact, in real life, you'll see conventional flow used by engineers and those that were in the British system, British subjects. So in Great Britain, they still use electron or conventional flow mostly. You'll see that in the colonies as well, like in India and so forth. If you see YouTube videos out of India or Pakistan or any of these places, they tend to use conventional flow. Electron flow is seen more commonly in colleges and at the technician level. And as I say, it works fine. You can understand semiconductors and diodes in all of the circuits using electron flow theory. The question then probably is which one is right? Well, they're both correct. This does explain how electricity works, and electron flow does explain how electricity works, and therefore they're both correct. And what I hope to prove in the next couple of minutes is that it doesn't really matter. All right, let's take a look at a simple resistive circuit. If I have a power supply here, and you understand that the long blade is positive and the short blade is negative, and if I have two resistors in series, and let's assume that they are of equal value, then I don't really have to give them a value. And let's say that this is a 10-volt battery. And now I'm going to tell my story in terms of electron flow. So electrons will leave the negative terminal of the battery, and they will flow in this direction through the two resistors and return to my power supply. In so doing, we know that current through a resistor drops or develops voltage, and I'll get into those terms in just a second. And so Kirchhoff tells me that they must all equal the total. So I know that 5 volts would be measured across this resistor, and 5 volts would be measured across this resistor. Now, if I want to discuss what is available in terms of voltage around this circuit, we can consider this negative terminal 0 volts. If I grounded my circuit, that would be no conflict, ground always being 0 volts, so fine. And we then know that over here, I would also measure 0 volts because this is just a wire. There is no difference, so that's my 0 volts. Using electron current flow theory terminology, as I go through this resistor, I develop 5 volts, and that then can be measured right here. And again, a resistor of equal value, it's the same current going through, same voltage is applied in total. So I will develop another 5 volts over this resistor, and therefore I will measure 10 volts here. The math of the two resistances adds up to the 10 volts, but also it adds up, we can verify, this is just a straight wire, and 10 volts was at that terminal, and so yes, I should be measuring 10 volts here in relation to ground. If I measure around the resistor, 5 volts. If I measure around the resistor here, 5 volts. But if I put my one lead on ground here, then I will see 0 volts, 5 volts, and 10 volts as I measure around the circuit. All right, that's described in electron current flow theory. I'm going to change my color, and I'm going to tell the same story from conventional current flow theory. So in conventional current flow theory, my current will flow from the positive to the negative. So from the 10 volts, I proceed through my circuit. I go through the two resistors, and I return to the negative terminal of my battery. And when I pass through this resistor, I will drop 5 volts. And similarly at this resistor, I will drop 5 volts. And so as we travel through the circuit, I could say I started with 10 volts, then I dropped 5 volts, leaving me with 5. I dropped another 5 volts, leaving me with 0. And this is where the term dropping comes. It seems to really make sense. So just to quickly recap, if I go electron current flow theory, I start with 0, go through the resistor and develop 5 volts. And then I go through the other resistor and develop another 5 volts, which gives me 10 and ends up with my total 10 here. So this is the difference between developing and dropping. It's just terminology. As I go through here, I go from 0 to 5. So I've developed the 5 volts. If I talk conventional, then I've had my 10 and I drop 5 and I drop another 5 until I get to 0. Okay. Let's up the difficulty level just a bit. We'll look at a diode circuit. All right, so You might say, well, that's fine and dandy for resistors because, you know, they're not a polarized device. It's not directional, all that. But if you have diodes, well, then the direction matters, right? Well, let's take a look at it. Once again, I'm a little crooked. I've got a power supply. This time I'm going to put a diode into my circuit. And I'll put a resistor to prevent current flow or to limit current flow. And let's go with my 10 volts again. Remember that it's much the same circuit, so this is my 0 volts. And in actual fact, I don't need to know the value of this resistor at all in order to give you precise voltages, and you'll see why in just a second. Let's describe this one in terms of electron flow. I'm sorry I switched the colors. Well, maybe I should go back to red for this, just to stay consistent. My electron journey begins at the negative terminal of my battery, travels in this direction. I develop a voltage over the resistor, and then, well, wait a second. I have to decide whether this thing conducts or not. Okay, how do I determine that? Okay, I have 10 volts on this side, and I have something less than that because it's coming from the negative terminal of the battery. I have something less on this side, so yes, current will flow. Okay, good. Then my current will continue to flow, and it will end up at the power supply. What are the voltages involved? Well, as a matter of fact, 0.7 is going to be lost over the junction of the diode, which means that right here I'm going to be reading 9.3 volts. And to tie it with the other one, here I'm going to measure 0 volts. Here I'm going to measure 9.3 volts. And here I would measure 10 volts. Okay. Let's take a look at this in terms of conventional flow then. And even though I've drawn the circuit in blue, this should still be reasonably clear, I hope. We start at the positive terminal, and we say, oops, we have a diode. I have to determine whether it's forward biased or not. Okay, so I have 10 volts on this side, and I have something less than that on the other side. It's forward biased. It will conduct. Notice I used the same voltage to determine whether it was forward biased or not. My current does flow through the diode. It flows through the resistor, and it comes back to my negative terminal of my battery. Now, I have dropped if I talk about conventional flow, I've dropped 0.7, which left me with my 9.3 here. I dropped 0.7 over the diode, leaving me with 9.3. Dropped another 9.3 over this resistor, and that left me with 0 back to my terminal. So once again, going one way or the other, we get the same results, and you realize that it doesn't really matter how you describe it, the voltages are always the same. And so then I can finish up by telling you how this matters in the real world. So if you're on the job, let's say, and you've got a circuit that you're analyzing, you're looking at the schematic and you want to understand what's happening with it, and it's you and a colleague, and I'm going to use the same circuit again. And so you're faced with this circuit, and you're discussing it, and in discussing it, your partner is saying or thinking that, okay, with conventional current flow, my current flows through the diode. I drop 0.7, which will leave me with 9.3, and I'm going to have 0 here. And this is what he's thinking to himself, and maybe he's even describing that way. You were in my class, so you're getting more used to the electron current flow theory, and so you think about this circuit and you say, okay, it's going to go from negative. I'm going to develop 9.3 volts over this resistor, so that's what I'll measure there, and then I'm going to develop another 0.7 volts over the diode, leaving me with my 10. And so you see, it doesn't matter. You're describing it in different ways. You can even discuss the circuit with someone using both methods at the same time, because what typically only matters to the technician is how did you get 9.3 volts here, and your question is, will the diode conduct? And you're both going to say yes. Which direction does the current go? Who cares? It's rarely important. Measuring current in a circuit, and this is probably, I can explain this at another time, but measuring current in aircraft circuits is a very rare activity. I would say 95%, if not higher, of your work will involve voltage checks. Well, your conventional flow buddy is going to come up with 9.3 volts, and you, with your electron flow theory, are going to come up with 9.3 volts, and you'll see that there is no conflict. Because all we want to know is, will the diode conduct? Yes. And we carry on. It's not going to be a question as to which way it works. Now, all that said, why do we even bother with it at all? Well, because to understand how these circuits work, in the process of learning how they work, understanding, like really slowing things down and following the current through the circuit gets the job done. I think that's how you started to understand about rectifiers. But hopefully this little session shows you that it's no big deal between the two. It's just a way of describing things. They're both correct and not a problem.